Hello students, in today's lecture we are going to start a new chapter, which is the superposition of waves. In this chapter we will discuss the results or the effects produced by the multiple waves which are arriving at a certain point at the same time. So this is a common situation when two or more waves of a given amplitude, wavelength and frequency arrive at the same point in space or exist together along the same direction. So several important cases of the combined effects of two or more harmonic waves are treated in this chapter. So the first situation is either the two waves results. We are going to discuss now the results of the superposition of waves. If the two waves are of the same frequency, either they are in different frequency, either they are in the same direction, clear? So there are different situations that results from the superposition of waves. For example, let us consider here we have two optical waves or electromagnetic waves. The first wave is starting from this point, which is the reference plane for the beam 1. The amplitude of this wave is E1 and these vertical lines are the wave fronts. Remember, the direction of the wave is always perpendicular to the wavefront, and this wave covers a distance s1 and it reaches this point. Similarly, the second wave starts from this reference plane and it is having amplitude E2 and it covers s2. When these two waves arrive at point P, then the combined effect will be discussed here. We will check either the direction, either the frequency, amplitude, and they are in the same direction or not. So there are different situations. If both the waves are of the same frequency, then it results into the interference of waves. The result is known as the interference of waves. If they are different in frequency while in the same direction, then the phenomena of beats will be developed. And if the two waves are having the same frequency but they are opposite in direction, then the standing or stationary waves will be taken place. So the topics which will be covered in this chapter will be: first we will learn the superposition principle, then we will discuss the superposition of waves of the same frequency and it results into the interference effect. Then we will know about the random and coherent sources. In the next part we will discuss about the standing or stationary waves which results from the superposition of the two waves of the same frequency but they are traveling in the opposite direction. And the next is the beat phenomena, which is the result of the superposition of two waves of slightly different frequencies. And at last we will know about the phase and group velocities. So let us know about more of the superposition of waves, let us consider we have this medium, let's suppose, and we produce two pulses. Let this is a pulse 1 which is traveling in this direction through this medium, and here is another pulse of different amplitude. This pulse is second. If the two pulses are traveling in the same medium, and after some time, as the time goes on, the pulses will approach each other. The second one is now reached here, while the first one is reached here, and a time will come when both the pulses will arrive at the same point. At that point, both will overlap each other and a combined effect will be produced here. So at this point we say that the superposition has taken place. After passing through this point, the waves, this is the second pulse, this is the first pulse, and this is the net effect produced by the superposition of these two pulses. And after passing through that superposition point, they will move forward as nothing has happened. This is now the first one, this is the second one. So here we consider that the two pulses are in the same phase. Either there are different situations that could be happened, either they are in the same phase, they have the same frequency, either they are traveling in the same direction or in opposite direction. So we will discuss all these situations step by step in this chapter. So first we are going to start the superposition principle. To explain the combined effects of waves successfully, one must ask specifically what is the net displacement psi at the point in space where waves with independent displacement psi 1 and psi 2 exist together. For example, if the displacement of this pulse from the equilibrium point is psi 1 and the displacement of this one is psi 2, similarly this one is psi 1 and this one is psi 2, or you can say the amplitude of the pulses. So we are going to know what will be the net displacement here at the superposition point. So for that we must know the superposition principle. The answer is given by the superposition principle, which states that statement: the net displacement of the resultant pulse, or you can say that wave, at the point of superposition is equal to the vector sum of the displacements of the individual pulses or waves. This means that if psi1 is the displacement of the first pulse and psi2 is the displacement of the second pulse, and when they approaches this point where the superposition is taken place, then the net displacement of this resultant is equal to the vector sum of the displacements of the individual waves. Clear? This is equation number 1. Using this principle, the resultant wave amplitude and irradiance, which is measured in watt per square meter. So the irradiance and wave amplitude can be calculated and verified by the measurement. The same principle can be stated more formally as if psi1 and psi2 are independently the solutions of the wave equation. Let's suppose we have a wave equation which is del square psi, which is equal to 1 upon v square into partial square psi upon partial t square. Clear? If the individual waves satisfies the wave equation, if psi1 satisfies this wave equation and psi2 also satisfy this wave equation, then the resultant wave will also satisfy this wave equation. Clear? Here this psi is equal to sum a times psi1 plus b times psi2, where a and b are constants. The superposition of the electromagnetic waves can be expressed in terms of their electric and magnetic fields by the vector equations. In case of electromagnetic waves, the superposition is expressed in terms of their electric and magnetic fields by the vector equations as E is equal to E1 plus E2, and for the magnetic fields, let's suppose that is B, which is equal to B1 plus B2. For example, we consider the amplitude of or the electric field of this wave is E1, while the electric field of the second wave is E2. So after superposition, the electric field of the resultant wave will be E, which is added according to vectorially. Similarly, for the magnetic field, they will be added vectorially. So when two or more light fields, so if we consider the electromagnetic wave to be light, then if the two light fields are of very large amplitude and they superimpose each other in a material medium, then the resultant light field may not be simply the superposition of the individual fields, because in their situations the interaction of the electric field with the material produces nonlinear effects. The possibility of producing high energy densities using laser light has facilitated the study and use of such effects, which is making the new branch of optics, which is called nonlinear optics. So we must remember that in a material media, the superposition of two light fields with very large amplitude the result may not be simply explained by the superposition principle. Superposition principle. Here I told that when two light waves of very large amplitude, they superpose each other in a material media, then at the point of superposition the resultant wave is not simply explained by the superposition principle, because that light waves with very large amplitude, they produce some non-linear effects in the material media, and that leads us to a new branch of modern physics, which is now called nonlinear optics. So that we will discuss later, I hope, in the laser chapter. Thank you very much for today.